Okay, so let's begin. Okay, so thanks everyone for joining again. So this is the video 2 of the lecture at UCL in the IRDM course. And the title of this lecture is Learning from User Interactions. And we've just completed the first part of the video talking about how do we understand user needs and tasks from their search query logs. And we're going to step on to the second and third phases in this part of the video. And in general, this part 2 of the video is self-contained. So if you haven't, if you're starting afresh from this video, then this part is self-contained. We're going to briefly summarize what we discussed in phase 1 and then start diving into phase 2 and phase 3. So essentially, this course is about developing an understanding of how these internet scale companies learn from user interactions. So essentially what happens is like a user has a need and task based on which they interact with a user-facing system, and the system then responds by offering some personalized content, and the users interact with that content. So that interaction gets logged, and based on that logged interaction, the system is able to understand whether or not the user was happy with the provided content and services. So essentially, this process allows large-scale systems to understand about users and help them in serving better content and better recommendations to the users for their needs and tasks. So as a logistical issue, the questions are, so I'm kind of hoping the questions will be posted on Slido. So there's a link to Slido. You can go and click on the link and enter the event code UCL talk. And if you post your questions there, I'll be happy to answer them until midnight of 19th of March, 2020. Cool. So if you look at the phase 1 summary, then on the left is the kind of topics we discussed in the first part of the video. So essentially, we started by asking this question that what exactly is a task and why are they important? And then we started by characterizing tasks across different interfaces like desktop search, digital assistants, and voice-only assistants. We then moved on to talk about how do we extract search tasks from query logs. And then we started by first looking at queries and their intents. We graduated to talking about sessions. And then we said that, hey, look, a session need not be an atomic unit, and a session may have information about multiple tasks. So maybe we want to focus more on task as an atomic unit for information retrieval. So then we proposed a few different models for search task extraction. Towards the end, we highlighted that a complex task could be decomposed into different subtasks. And then we looked at some different ways of developing these hierarchies of tasks and subtasks. And so most of the discussion in the previous video was talking mostly about how do we extract tasks from a web search perspective. But then in recommendation systems, if you go to the Spotify homepage or Netflix homepage, then the user need not enter a query and the recommendations have to be served. So essentially in those scenarios, we still have to identify user needs and user intents. So we looked at a couple of case studies at Pinterest and Spotify and how these systems go about understanding and predicting user intent and using it to better serve the users. So the take-home messages from the last video and the first phase of this lecture are that it's important to consider user needs and tasks. There are different granularity in a web search system at which you can understand these needs. There's a query level granularity, then there's a session level granularity wherein you're looking at multiple queries in a session, and then there is a task level granularity wherein we are saying that can we identify the task and all the queries which help solve that task, and then do this task extraction system to help better serve and understand user needs. And then finally, beyond recommendations, it's important to understand and extract user goals and intents. And for that, we kind of motivated the need for developing a quantitative as well as like a qualitative approach for that. So broadly, we have looked at how do we try to understand and predict what the user goal and user need is when they come and interact with your system. So once we have identified what the user goal and need is, then we can look at holistic user interactions and then try to learn from those interactions. And this is where in the phase 2 of this lecture, we're going to talk about learning representations. So essentially, an important part of any user-centric system, which are being developed at industry scale across different domains, is that we want to be able to represent a user's preferences and user's interest in a compact representation. Now, based on these representations, we can then develop content recommendation techniques, and we can then develop our recommendation and ranking systems, which would help identify the right content to serve to the user. So in this phase, we're going to start by looking into some of the existing approaches in which how different companies and different academics have looked at learning representations of users. So we're going to start with talking about what sources of evidence there are. What is it? What type of data is it? Do we have available about users which can help us learn their representations? We're going to start with some traditional vectors and topical profiles and entities which have been used for almost 2 decades. And then we're going to nudge towards more recent state-of-the-art approaches using collaborative filtering in a neural setting, coupled collaborative filtering, deep collaborative filtering, and then briefly talk about embeddings and different embedding-based approaches. We're going to talk about short-term, long-term profiles. We're going to talk about group-based representations in a cold start setting. And towards the end of this phase, we're going to talk about some really recent published state-of-the-art methods on multi-view and multitask learning systems. Okay, so let's start by posing the question that we have to learn a user model, a user representation, and where do we start? So what kind of data can we be looking at, can we consider to learn these user representations? So one of the important sources of evidence is around content. So the content could be the kind of queries the users have issued. So the query text for all the past search queries the user has issued could be as the data from which we build the user representations. It could be the content of the web pages they visit. So if you're looking at a browser history of the user, or if the user has visited some pages on your social media platform, then that's the kind of topics and data which the user has demonstrated interest in. If you're looking at e-commerce websites, then the product metadata and the categories of purchases the user has done in the past are information sources which can help you develop some of your representation learning approaches. So again, what you can do is you can look at the content of historic interactions and then maybe extract topics or find out different categories and create a vector of interest profile of the users based on the historic content they have interacted with. Now, beyond content, there is behavior data as well. So behavior data can be decomposed into 2 parts. One is explicit feedback. So we can ask users that, hey, do you like this category or not? Hey, do you like this topic or not? Do you think you would be interested in getting recommendations about this topic? Now, this is very costly to obtain because at scale, you cannot ask like 1 million users every time whether they would want to kind of consume such type of content or not. On the other hand, implicit feedback is super useful. So implicit feedback means that we're not explicitly asking the user, but then we're observing how they're behaving. So in a way, when we know how users are behaving, then we can look at whether they're clicking, whether they're coming back, what kind of pages they're visiting, what kind of products they're adding to basket, what kind of products they're purchasing, what kind of products they're viewing, and so on and so forth. So that behavioral data provides a lot of cues about users and their preferences. And also, additional thing to consider is the context. So there's always context involved because all these recommendations and search rankings are contextual. So it depends on the location, the time of the day, the device you're interacting with, and a host of other different contextual features. So beyond the source of evidence, we can also look at like different time frames. So we can look at like short-term and long-term preferences of users. And like there is a lot of like persistent user activity or recurring purchases, which indicate long-term interest, whereas there might be a new event in the world right now, and the user might start querying about that event. So these are maybe like one-time queries, one-time purchases, and they're like sudden spikes in interest, which are not going to sustain for a long period. So again, like when we're constructing user models, it's important to understand at what time scale are we looking at, and what kind of what temporal granularity of the data we should consider when we are developing these user models. And finally, like who are we developing it for? So if we really want to do scalable personalization, then really we have to learn these individual user profiles and finds, which helps us finding similar users. But if cold start is a problem, let's say, then we may want to do a group-based personalization, like learn user representations and user profiles for user groups and user cohorts. So we're going to touch upon a group-based recommendation problem in about 5 minutes from now. Cool. So we have seen like what kind of data we could use to construct some of these representation and embeddings of the users. So now let's just kind of walk through that if we have access to this data about user interactions in the past, the historic interactions, historic content from the user, then what kind of different approaches we could use to learn these representations about users. So the first and simple thing to do is bag of words, right? I mean, so everybody knows this. We can look at all the different words the user is looking, and the user has maybe typed in the search query or the different product metadata, the text from the product metadata, and then create like a bag of words profile. And then we can do like a TF-IDF on top of it, which will give us a representation of the user to work with. So the TF-IDF weighted would be term frequency multiplied by inverse document frequency. And so essentially this will give me a distribution over all the terms in my vocabulary. And then I can represent each user based on the TF-IDF vector based on their content in historic content data. But then like we can do a lot more. And this is where like we start by looking into topical, profile, and entities of interest. So essentially we briefly touched upon like LDA type of models, wherein we say that, look, you can learn in an unsupervised manner what are the topics. And essentially what you're going to do is say that each topic is a distribution of a word, each document is a mixture of corpus white topics. And essentially like each word is drawn from one of those topics. So what we can do is we can learn, we can take a bunch of historic content data about users and pass them through an LDA inference, which will give us a distribution of user interest across these topics. So it's a two-step process. Like in the first step, you train an LDA model on top of some data, which will give you topics. And then for each of the users, you collect all of their historic content in a document and then run it through the LDA inference model, which will give you a distribution on the set of topics for this particular user. So that's your k-dimensional vector, which you will use for all your recommendation and search ranking problems. Now, again, like the same, we can learn. So once we have extracted the topics, we can learn different distributions across for different users. And so we can apply topic modeling, not just in terms of text, because LDA and these latent variable models are really like very powerful models which can be applied on any type of data. So if you apply on like jewelry images, then if you're able to represent each of these images in some feature space, so essentially then what it means is you can apply LDA on top of this image data set, and that will give you essentially some topics around the different types of jewelries and different types of image fashion features. And this is like, again, like one of those clusters in the LDA topics could be jewelry, the other could be maybe some women tops. So essentially this says like the LDA style approaches is really generic. So we can apply it over text, we can apply it over metadata, we can apply it over images, and so on and so forth. And a lot of these like startups and companies have scaled these approaches to a good scale. And interestingly, the one of the very nice things about some of these latent variable models is that it's very extensible. So in the last 10, 15 years, a lot of research has gone into developing custom latent variable models for the different problems we'll face. So again, the data generation distribution can be changed, and we can build LDA for images, social network, music, purchase histories, computer code, genetic data, click-through data, and so on and so forth. So these latent variable models really provide us with a way of encoding our intuition about models in a very specific way. And given that, like in the last 2 or 3 years, a lot of work in the probabilistic programming world has gone into developing these programmable solutions. So instead of going back and writing an MCMC or GIP sampler for some of these latent variable models, now we have the ability to pose these problems as a probabilistic programming question. And then there are like inference and solvers available off the shelf, which we can use to kind of code up these latent variable models. One of the other things is TensorFlow probability is also pretty good and like helping us encode some of these like distributions in a TensorFlow graph. So that's, yeah, if you're interested, you can look up TensorFlow probability and kind of dig deeper into it. Again, so when we have looked at topics, then an interesting aspect arises that users' topical interests change over time. So again, there's some work coming in from M&A's research group a couple of years ago around topics changing over time. So then instead of having a fixed latent Dirichlet model, you have a time varying model wherein like there is like an interaction effect happening across different parameters, which are kind of shared across different time slots. So here, if you look at the figure on the right, then each slice over here is one LDA, and then you have like subsequent slides, which subsequent slides, which each of which is like is valid for a given time t, and then there is like dependencies across these parameters across different times. Okay, so again, some other recent work has kind of looked at explainable user clustering. Again, it's an extension of the LDA model over time, but specifically for short text. So that's the paper at SIGIR 2016, if you want to look into it. So far what we have done is like, we've looked at some sources of evidence from users. We've looked at some traditional vectors, some topical profiles, and then now we start looking at some collaborative filtering style approaches here. So collaborative filtering is pretty old. It's been around for like almost 1.5 to 2 decades now or more. So essentially what it says is that if I have information about the user and if I have information about the items, then maybe I can create a matrix out of it. And I can do a decomposition on the matrix to give me the user and item representations, which I can use to do some recommendations to find the most similar users, might find most similar content. So essentially what it means is you'll have to create a matrix, which is of the scale of the number of users. So if you're a big company, then you'll have like millions of users. So you're looking at a huge matrix of 100 million users across like 50 million items. And then you're going to do a lot more of approximations, approximate factorization techniques to kind of make it work at scale. So this matrix factorization solutions kicked off way back in 2008 when the Netflix $1 million movie challenge was released, and then a lot of good performing solutions were based on these matrix factorization style approaches. But interestingly, what people realized was that matrix is just very restrictive. So I can create tensors out of these matrix. So matrix is essentially like a 2D array, but what we can do is like, what if we create an n-dimensional array? And that array would mean like I'm extending a matrix to an n-dimensional tensor. So an example over here would be that, let's say that if you see the tensor A in this figure on the right, that essentially is a tensor, which says that we have one dimension as the user, the other dimension is the locations, and then like activities. So again, like we can create a tensor of any number of dimensions. So this 3D tensor is shown over here, but then like there's nothing stopping us from creating even more dimensional, like 4-dimensional, 5-dimensional tensors, and then doing like tensor factorization on top of it. So essentially, what we are saying here is that we're going to extend the matrix to a tensor, and then we're going to include a lot of information about the user, items inside information, and then do a tensor decomposition, similar to how we did matrix factorization to kind of learn some of these representations. So this is where like we did some work a few years ago on task-based user modeling. So essentially, we're saying that so far, people know that we can create user representations using topics, but we can also do that with task. So the goal here is that, hey, can we combine the topical profile of the user with the task they do? So essentially, we've been in the first part of the video today, we saw that understanding user task is important. And if we know that some users are interested in these tasks, then maybe that can help us develop better user representation models. So essentially what we did was we said that we're going to do a user topic and task tensor. So we're going to create a 3-dimensional array and call it a 3D tensor. And that is going to contain information about the users, about the topics they like, and about the task they have kind of interacted around the kind of task they have solved with the system. So then we can do tensor decomposition style approaches. And one of the interesting things about this is that now we can play around with like tensors and matrices together. So what we've done in this paper at ICTIR in 2015 is that we have created a user topic task tensor. And then you said that you're going to share the user dimension with another matrix, which is like a user and term matrix. So now essentially we have a tensor which is shared in one dimension with the matrix, and then we can do a joint coupled matrix tensor factorization. So again, there's like a toolkit which you can use to kind of do some of these some of these decompositions, which will give you a more richer representation of the user. So taking a step back, what we've done is like we started by saying that we can create a matrix and then we can decompose it, learn the vectors. Or we can improve on the matrix and say that we can create a tensor and then decompose it. And we've gone even a step further and say that you can then do a joint decomposition of tensors and matrices and then learn representations out of this. So essentially what we're saying is we're encoding the data, more and more data in richer structures, and then doing decompositions on it with the hope that the new representation is a lot more richer than the previous representations. And now once we have these representations, we can go back and maybe do a nearest neighbor search and find the most relevant products or relevant results, and then do personalized content recommendation to users. So one of the other recent approaches which have become popular is extension of these decomposition and factorization approaches to neural models. So essentially, if you look at a traditional matrix factorization, then they essentially rely on inner products. And inner product is a linear multiplication of latent factors. So the core behind a matrix factorization is this linear multiplication of latent factors, which we learn about the users. But if you take a step back and say that the last 8 years of progress in the deep learning community has said that we can do amazing sorts of like nonlinear factorizations and we can introduce nonlinearity into our models, and that gives like tremendous benefits. So then there's this very nice paper in www 2017, which says that maybe we can replace this linear multiplication in matrix factorization by a nonlinear component. And then we could then couple neural deep learning with like collaborative filtering. So essentially, what we end up with is nonlinear interactions across users. So this neural collaborative ranking is an approach which combines the benefits of the deep learning, nonlinear functions from the deep learning community with the matrix factorization style approaches. So essentially, it's doing a combination of nonlinear interactions and a matrix factorization style element-wise product. So then it's going to give you the benefit of doing collaborative filtering as well as nonlinear modeling using the deep learning networks. So while we're talking about neural approaches, instead of just combining it with collaborative filtering, we can also start by looking at how do we create these embeddings how do we create these embeddings of users and content? So rolling back to 2013, there's this like very nice paper from Thomas Mikolov saying that we can learn embeddings of words. So, I mean, he proposed this continuous bag of words model wherein we can learn world-wide representations. And the goal here is like, if two words co-occur together, then we're going to push their embeddings closer in the representation space. And if they don't, then you're going to do some negative sampling and then push two words different, far away from each other in the representation space. Now that idea is very extensible. And what we can do is we can apply the same idea to products. So there's a very nice Rex's 2016 paper that says that we can learn product embeddings using some of this approach. So Criteo and Facebook AI Research did some work around learning this product metadata embeddings. So we can look at the metadata of the product and then try to apply some of these word-to-vec style approaches to that to learn those embeddings for the products. And what we can also do is like essentially use the metadata along with the product description to learn some of these product vectors. So now when we are learning these embeddings, so there's nothing stopping us from learning the embedding of the user and content together, right? So far what we've done is we've just picked up the user information and then learn a representation for the user. In matrix factorization, we've tried to learn the representation of the user and item together. So essentially, we can then just do a full neural model to learn embeddings of the user and item together. So one of the papers at Wisdom in 2017 was doing this joint modeling of users and items. So essentially, what they propose is a deep cooperative neural network, which has two parallel networks, as you can see in the figure. So you have the user text and the item text, and then you're going to learn some parallel networks, which are then trained via a joined shared layer of loss functions. So then, like now again, since there are these like neural network blocks, you can do a lot more Lego style building together. So you can enforce some of these representations to be closer, or you can share some layers and then do a lot more playing around with like architectures which jointly learn these user and item representations. This is what we ended up doing for one of our research projects a few years ago. So we are saying that since a lot of people have learned these representations, then maybe we can learn task-specific representations. So what we did was we looked at the word-to-vec embeddings and said that we're going to learn task-specific embeddings. So as you can recall from the previous video in the first phase of this lecture, there is a lot of insights in the task context. So maybe if you're looking at, let's say, a user search stream, and if the search stream is like consists of queries like Facebook, GRE exam, Coldplay music, GRE syllabus, Paradise video, and then a mock test, then if you're looking at a simple word-to-vec, then a simple word-to-vec will just concatenate all these queries together and then try to bring the words closer. Now, the problem is that this session is really a multitask session. Like there are three separate tasks. The first task is about Facebook. The second task is about finding information on the GRE exam. And the third task is about Coldplay music. So if you're learning your embeddings using a session context, then your embeddings are going to get polluted. You're gonna bring the GRE exam and Coldplay together in your representation space, and that's not what we want to do. So now if we have task information, then we can tease apart these contexts and use only the on-task queries as part of the context window when you're training your word-to-vec models. So essentially, you can play around with what sort of context gets fed into your word-to-vec models, and then you learn like different embeddings. And we saw that like if you do a task-specific embeddings, then you're able to learn a lot more better in terms of search, and it gives you like a lot better query suggestions and related searches. Cool. So a brief summary so far is that we've started by looking at user representations, and we've said that collaborative filtering is nice. We can combine it with neural collaborative filtering. We can learn neural embeddings. We can learn embeddings of users, products. We can learn joint embeddings of users and items, and maybe we can learn like task-specific embeddings. So one of the other interesting and important aspects which researchers have considered is short and long-term profiles. So essentially, like if you look at the figure on the right, then the profile of the user, which we can construct, is based on how far in the history you want to go in order to construct this user profile. So again, like we can look at only short-term context, or we can look at like long-term preferences, or we can look at a combination of those. So there is some work coming in from Microsoft Research at SIGIR in 2012, which says that you need a hybrid model of in-session and short-term context personalization, and combined with like historic long-term interaction data to learn your profiles of the users. Now, this was like this was more like a hard-coded way of determining like what is short-term, what is long-term, and how do we combine the two. So interestingly, like with the progress in neural models, we can do this sort of like long-term, short-term combination in a more principled way. So there was this nice paper at KDD a couple of years ago which says that if you're doing a session recommendation, then I can apply an attention layer on the session. So maybe you're looking at like a sequence of user interactions in the last 1 week. And if you have an attention layer, then the attention layer decides which of these historic interactions is more important in the current session. So essentially, like, yeah, I mean, we get the attention model allows us to capture correlation between the target items and the long or short term memory of the user's interest. And this kind of scales very beautifully and kind of gives pretty good results. So beyond short-term and long-term profiles, there is also this issue of cold start and cohort-based representations. So essentially, if you look on the left of the plot of the figure here, then maybe you can learn like a global representation of all users, or you can learn like individual specific representation. But the problem is like the global model is not personalized. The individual model is hard to scale. And if you have new content, new documents, new users, it doesn't work well. So maybe this is where we could do a lot more of cohort-based modeling. So cohort is just a fancy name for user groups. So essentially what we're saying is that maybe we can look at user groups and then learn representations for some of these user groups together. So there's a paper at SIGIR in 2014 from Microsoft Research and Bing people on how do we do like cohort modeling for better personalization. So essentially, a cohort could be defined as a group of users which has shared characteristics like these users are sports fans, so maybe I'll do search re-ranking based on whether or not the user is a sports fan. So again, users can belong to multiple cohorts. You can, of course, be both a sports fan and a video game fan. And a cohort has some cohesiveness that, like, if people in this cohort search for FIFA, then most likely they click on FIFA.com. Versus if people in some other cohort search for FIFA, they click on something else. So you can use a lot more insights from the group of users you are with to kind of better do re-ranking and personalization of results in search. So then the goal would then be like that, how do you estimate individual preferences based on cohort preferences? So the plot on the right gives you a way of combining the individual preference with the preferences of the cohort. And then you can vary this parameter. Like if I know nothing about the user, then I'm going to rely on features from the cohort. But if I know a lot about the user, then maybe the features from cohort are not that useful for me. So again, it depends on like how much data do you have at your disposal for each of these users. Cool. So another aspect to consider here is multi-view representations. So oftentimes what happens is that we have different types of data for different users. So again, if you're looking at some users on online portals, then you can look at the text of the messages they posted. You can look at their neighbors in the social network, or you look at the articles they link to. You can look at the articles they like, the videos they consume. You can look at the images they upload. So again, all these gives you different type of information about the user, but essentially it's the same user, right? So if you're looking at multiple types of interactions from the user, then all these essentially point out to the different views of the same user. And here comes the problem that like if you have multiple views, right? I mean, one of them is text modality. The other one is a social network of who these people follow on Twitter, or what kind of followers do these users have. The other one is like the images to interact with, the videos to interact with. So again, you're looking at this holistic multi-model data of each user. And this is where you could say that I'm going to do multi-view learning. So a multi-view model will learn a single user vector, which is capturing information from across each of these views. So instead of like separately training out my representation learning approaches for text separately, for images separately, and from social network data separately, I'm going to say that the user is going to have a single representation, but then this representation is shared across the different views of the data. So if you look at the equation on the bottom of this slide, then you're doing, if you're assuming that you have the user, which is represented by UI, but then you're learning the representation using I different views of the user as such. So yeah, so you can do a differential weighing of each view. Like one view might be more important based on maybe data sparsity, that we may not have enough data from the image view, so I'm not going to give it a lot more weight. I have a lot of data about the messages and text, so I'm going to give it a lot more weight. So you can play around with like how do we decide the weights for the different views. Essentially, we are doing again like a joint decomposition uh, in a multi-view setting here. So when you're looking at multi-view, so the previous approach was really solving it in an optimization way, right? I mean, we're creating a loss function, we're creating like a maximization, minimization objective, and then solving it. What you can also do is like we can do deep like multi-view as part of a deep learning solution as well. So there's some work coming in from Microsoft Research at www in 2015, which says that we can create these multi-view embedding models. So now if I have a user and if I have like item views, then I can have like parallel neural architectures and neural networks, which will each give me some information about the different views. And then we can train them jointly to learn a multi-view representation. So again, like the core being that if you have one view of the user or multiple views of the items, you can create these like parallel network architectures, which will allow you to learn from the different views of the user. Finally, we look at multiple tasks. So multitask representations are essentially saying that maybe we can learn representations about a user from different tasks. So learning from multiple tasks can be more effective to reflect their interest across different tasks. And it might also be like a bit more generalizable to new tasks. So especially in the NLP community, a lot of recent state-of-the-art results have shown that if you're training a model, then don't just train it on a single task. If you train it on multiple tasks, then the model has a lot more generalization power, and the model is learning across multiple tasks in a very good way. So there's a nice paper at KDD in 2018 looking at learning user representations from multiple e-commerce tasks. So if you're in an e-commerce portal, then your task could be like, are you clicking on the item or not? So that's one prediction task. Are you saving this item for later? Are you purchasing this item or not? Are you coming back and viewing this item and product? So again, like each of these are different prediction tasks. And instead of learning like models separately for each of them, there is enough motivation for us to learn a joint multitask model which predicts all of these together. And one of the great examples of this is some recent work coming in from Google. So this is essentially from the YouTube team at Google. And this is a very, very recent Rex's 2019 paper, which talks about like what video should we show to you next. So if you look at the plot on the left here, so there's this YouTube has this feature of the next video. And essentially what you can do is you can train a multitask model here that instead of predicting one interaction about the user, I'm going to predict whether the user is going to like the video, whether the user is going to comment on the video, how long is the user going to stream this video, is the user going to stream this video at all or not. So again, these are some tasks which I can try to predict about the user, and then look at variants of multitask architecture to predict these, and then decide on how do we recommend the next video, which video should we recommend next in the YouTube portal. So again, like if you look at the paper, then they talk about some mixture of expert style approaches in which you can really exploit the advantages of multitask learning. And multitask learning essentially gives you the power that you're now learning across multiple tasks. Maybe some of these tasks are helping each other out, and then maybe you're learning a lot more generalizable model than the model you learn when you train one task at a time. So that was a quick 35-minute view of this topic. And so essentially this phase two here was about learning user representations. And the take-home messages here being that heterogeneous information sources about the users help in creating richer user profiles. And there are different ways of representing users, like task, topics, embeddings. You can jointly train models. You can train multi-view models. You can train it on multiple tasks together. And each of these will give you a better representation of the user. And the different tasks capture the different aspects of the user preferences. So essentially, what this means is like so far that we know that the user is coming and interacting with the system. And based on the historic interactions, we can create these user profiles of the users using some of these approaches. And then I can use this profile in search re-ranking, or I can find relevant content to surface to the user and do it in a lot more personalized manner. So now we're going to talk about where we are in this journey. So just going to take a small break. Right. So we're talking about like how do we learn from user interactions, and we started by looking at how do we infer the user task and need. So why are they interacting with the system? What's their need? What's their goal? What's their task right now which they're trying to accomplish? So in phase one, we developed some models for understanding these user tasks and user needs. In phase two, we talked about like just now, like how do we learn these representations about users, which help us offer personalized solutions. In phase three, we are essentially going to talk about large-scale experimentation and metrics, which help large-scale industrial machine learning systems to make incremental progress towards like better serving the users. So in this part of the talk, we're going to talk about like how do we look at these logged interactions and how do we predict user satisfaction, which are the two things towards the right on this figure at the top. Cool. So this phase is titled Leveraging Interactions for Metrics and Experimentation. And essentially what it means is that when users come to your platform, then they leave behind fine-grained traces of interaction signals. So they might be clicking around, they might be moving their mouse, they might be scrolling, they might be clicking, reading something, coming back, they would be spending time on your platform. So you can observe and log a lot of these like behavior interaction data about users. And the goal now would be that what can I infer about the user based on this data? And can I say that, yeah, based on this, I think the user was happy. So I'll give my model a +1. Or we can say that this interaction says that the user is not really happy. So then the model is going to get a -1. And then we can compare which models perform well, how are we systematically making progress towards better models in these like industrial systems. So explicitly, we're going to look at like 3 different topics here. So in the first topic, we're going to talk about explicit feedback, that how do we collect judgments from the users. And then we're going to say that, look, explicit feedback is not really feasible because you cannot ask like 1 million users. You can only ask like very few. You don't have the budget to do that. So then industrial systems heavily rely on collecting implicit feedback to kind of train their models, to evaluate their models, and so on and so forth. And then we talk about like how do we use all this data to predict user satisfaction and kind of evaluate models at scale. Again, if you have any questions, there is a Slido link which you can use and post your questions there. So metrics and experimentation. So there's this famous quote by Lord Kelvin saying, to measure is to know. If you cannot measure it, you cannot improve it. So I cannot emphasize enough the importance evaluation and metrics play in any industrial machine learning system. So essentially, developing the core cool ML model is just part of the problem, right? I mean, there's this huge effort around understanding how the model is performing, what type of users is it good for, what are the problems and fallacies in the model, where should we improve, how do different models compare and contrast with each other. We have a current model, we have a new variant. Should we release a new variant to the users or not? So again, these are a lot of important questions which any day-to-day data scientist or machine learning engineer or researcher face and kind of has to deal with and has to develop an understanding around it. So my goal in this phase of the talk is to give you an overview of what are the different problems which arise in this kind of work in some of these like industrial machine learning systems, and how do we start to think about some of these. So we start with explicit feedback. So the goal is for us to find out whether the user was happy with our recommendations or with our rankings or not. So one of the things we could do is like explicitly ask for feedback. So who do we ask? So the first point over here is that we can ask judges or annotators. So essentially what we're going to do is that, let's say we're talking about a search engine. So we have the user typing in a query and we show them a set of results. So what we can do is we can take a snapshot of that and then go and ask some of my Amazon MTurk judges, or I could have some annotators, and I'll show them this screen that, hey, look, the user came in, this is the query they issued, this is the results we showed, and this is the click information. Do you think whether the user was happy or not? So a judge, which is a human judge, can look at the queries, look at the results, and see whether or not they were a good match or not, and then provide a judgment. So judgment could be like +1 or -1 that, oh yeah, I think this is a okay result and the user should be happy. Or they can provide a judgment on a scale of 1 to 5 that I think like the user was really unhappy with this because they never clicked on anything. So it could be a 1, or the user was super happy, it could be a 5. So they can provide a rating. So essentially what you're doing is you're asking about a user's happiness with the results from a judge. Now there are caveats here, right? There's a problem that, I mean, the judge doesn't know what the task was the user's trying to do. So even though this like annotation is coming in from a user, from a human, but then they were not the ones who issued the original query. So there's a problem here. So this is what you can kind of address by doing some lab studies. So you can invite a bunch of people in and ask them to perform tasks, and then you can subsequently interview them to get feedback on satisfaction. So this is a sort of like gamification. So what I'll do is like I'll invite like 10 people in and let them use my search engine and let them issue their queries and then interact. And then at the end of it, I'm going to ask like, were you happy with it? How satisfied were you with the results? Now this is a bit better because you're kind of asking feedback from the users who interacted with your system. But the problem here is like, this is a very lab setting, right? So I mean, on a day-to-day basis, I'm like running in the wild, right? I'm in the world, I'm in the office, I'm querying. So that general context and scenario is very, very different from when you ask somebody to come in and sit on a laptop in a lab and then query search engine. So again, like there is some generalization issues with these lab studies as well. We can also do like field studies. So a field study would be a bit more general. So essentially what we could do is like maybe we can install a toolbar. So maybe there's a Chrome plugin which I can install, and then every time I complete a search session, then the Chrome plugin will ask me that, hey, are you happy or not? So this is a bit more general because at least you're not like bringing people in or asking somebody else. You're asking the user, and you're asking them once they have kind of really solved their information need, and they can then provide the best feedback. But again, like there's an adoption problem here. So we cannot like always, we cannot make 100 million people use your Chrome browser plugin and kind of answer some of your questions. So again, there's a problem because none of these approaches allow us to collect feedback from a large set of users. So when I was interning with Microsoft Research, we collected use feedback from about like about 1,000, actually about a few hundred users, because again, like scalability is a problem. We cannot get true explicit feedback data from like 10,000 users. That's not possible at all. So one thing which we could do if you're a live system, if you're running production models, is that you can do A/B test. So A/B test is essentially a way to collect feedback signals from the user. So essentially what you do is in an A/B test, you have your set of users, you have two models you want to test, and you're gonna divide your user groups into two halves. So you're randomly gonna assign some users to group A, some users to group B, and then you're gonna see like which user are more happy. So you can do some sort of A/B testing to collect some data about your models as such. So I think like as we've kind of realized so far that collecting feedback explicitly is hard and it's not scalable. So that's why a lot of these companies rely heavily, very heavily on implicit feedback. So implicit feedback means that we're not explicitly asking the user whether you were happy or not. We're kind of relying on making interpretations from their interaction signals. So we observe how the users interact. And based on those observations, we decide that, yeah, we think the user was happy or we think the user was not happy. So this heavily relies on interaction signals and logging some of these interaction signals. Now, what sort of behavior signals can be logged? So, I mean, whatever, like if you have more sensors, you can log literally everything. So in web search, people have been logging search queries, the clicks, the mouse movements. So if you're scrolling, then the mouse pointer location will be stored for any given point of time. So your search session on Bing.com would mean that you issued a query, so they log the query. You clicked on a few results, so they log the click, but they also log your cursor movement. So you started from position X, Y at time T1, and then you kind of have this like time series of the cursor coordinates across a period of time. So that's the granularity at which we can log some of these interaction data at scale across like 100 millions of users. Now in mobile devices, we can log the attention, like are you scrolling or are you viewing the current viewport, the current real estate on your phone, or we can log the voice interactions and so on. So this is where we start to look at looking at different interactions and then trying to predict whether the result we showed to the user was relevant or not. So the underlying goal in all of this work is we observe what the user do, we log those interaction features, and then we try to infer and assign labels to our data that if this result was a relevant result to this query or not for this user. So if, let's say, the user clicked on a result, you go to google.com, you type in a search query, you get a result. If you click on the result and then you spend 2 minutes reading that result, so then that means you were happy with it because you spend time and effort reading it. And that is the data we want to use, because then that means that result is relevant versus if you go to a result, you look at it for like 2 seconds, 5 seconds, and then realize, no, this is not what I want. Come back to the search result page. Then that means that result was not a relevant result. So this data provides us like with implicit labels, which we can use to train our rankers. So for the first result, I'm going to give it a +1 because we think that the user liked it and interacted with it and read it for 2 minutes, versus the other result where we know that the user didn't really like it. So it's going to get like a -1. And now we can train our search ranking models with this implicit large scale data. So what we're going to do now is we're going to look at some specific examples of what kind of data do we log and how do we use them to predict some of these things. So there's this nice work at Sequoia 2013 looking at mining touch interactions on mobile devices. So when you're looking at mobile devices, then we can log a lot of like temporal and touch features. Like temporal features would be dwell time, that how much time did you spend viewing this page, versus touch features like did you apply a pressure on the result, or what is your touch size, like how frequently did you touch your screen. We can also look at some zooming and swiping features. So are you zooming in to read something, or are you like quickly swiping and like you don't like the results or whatever. So we can log all of this like zooming and swiping interaction features based on how you interact with your mobile devices. We can also look at like inactivity and transitions. So if you're inactive for a period of time, that means you're consuming content which is shown on your screen right now. And you can transition from one page to the other. So you can click on the result, go to some other page, come back, and move around in different parts of your app. So these are all like important transitions to consider. So this is the kind of features we can log from your interactions. And then once you have these features, then you can train like your prediction models. So essentially what that would mean is that if I log some of these features, then I can create a Markov chain for transitions across interactions. So essentially the user started the page view, and then maybe they swiped, they clicked on something, they came back, they zoomed in, and they swiped again, and then they ended the page view. So that will give us a transition sequence to work with. And then what we can do is like we can look at each of these features and then see the correlation between some of these. So what we do is like we can collect this implicit feedback across like millions of users at large scale, because this is essentially logging which we do at our end. And we can like maybe we can ask like a small set of 100 users that were you happy with this session or not. Once we have this data, then we can do a correlation between the implicit feedback signals and the explicit feedback signals. So essentially what we're doing here is we are combining the two. So we are saying that, let's say you're using the Spotify homepage, and to maybe a subset of users, we throw a survey that when you are interacting on the homepage of Spotify, we pop up a survey to ask like, hey, you just had a home session. How happy were you? Or were you happy or not? So then maybe let's say like 10,000 users responded. So we have a 0 and 1 response from these 10,000 users. So that means 10,000 users told us that those sessions of the user were happy or not happy, satisfied or not satisfied. So that's the explicit data. So that's the gold standard label data, which we can use to train our models to evaluate different implicit signals. So for the same 10,000 users, we go and look at our logs. And the log would contain all of these like interaction features, which we have kind of quantified and stored. And then we can do a correlation that we think that dwell time was positively correlated with satisfaction. So that's a good signal for us to consider. Whereas some other like scroll and swipe frequency was negatively correlated. So that's like a dissatisfaction signal, perhaps. So this is how a lot of these like companies rely on collecting large scale implicit feedback and using small scale explicit feedback to infer which of these implicit feedback signals are important. Now, let's say based on this figure, I pick up two. I pick up like dwell time because we think it's positively correlated with satisfaction. And we pick up like scroll frequency because we have seen that this is negatively correlated with satisfaction. So now once we have made this claim, we can use these dwell time and scroll across all the 100 million users and then label each of their sessions as a satisfying session or a dissatisfying session. So this is the core of it. So we are relying on these logged signals, and we are relying on explicit data to tell us which of these signal is important, which of these means positive, which of these means negative. And then once we've decided that, then we use that to tag and label all the other like millions of user interactions which we have seen historically or which we are going to see in the near future as well. So once you do this, then essentially you can look at all your 100 million users and say like which users were happy and which users were not, and then you can kind of compare different models and different approaches. So that's really the core of what goes on behind the scenes in some of these large scale evaluation of ML models. So I'm going to walk you through some of the examples of what it looks like in the same thing, the same concept that we log implicit features. We use them to develop metrics and evaluation using some sort of like explicit data. And we're just going to see some examples of this in like different search and other applications. So this is nice work at SICM in 2012 on predicting web search success with fine-grained interaction data. So essentially, these authors started by logging the cursor movements. So essentially, what you can do is like you can follow where the cursor is going, and you can create like mouse cursor heat maps, which are going to provide you information on where the user is looking at or interacting on the whole search result page. And then once you have this, then you can create some of these features like what is the query, what is the clicks, the number of clicks, the number of clicks over the queries, the total number of clicks in the entire view. You can look at like time features like start time, dwell time, average time, and so on. You can also look at cursor features like what's the average y coordinate, what's the average x coordinate, what's the acceleration of the cursor, what's the velocity of the cursor. So you can extract a lot of these cursor and click features as well. You can also kind of like log and consider scroll features. That are you scrolling? What's the speed of scrolling? What's the velocity? What's the velocity of scrolling? Did you scroll at all or not? So like you can look at some of these scrolling features as well. So again, like these are some examples of what kind of features we could log and kind of consider to evaluate whether or not the user was satisfied with our content recommendations and rankings or not. Now, if you notice, then a lot of this heavily relies on looking at clicks. That if you're clicking something and then if you're spending time on it, then that means you're happy. If you're not clicking, maybe you're not happy. But the problem is like click is not always present. So if you search for, let's say, Snapchat stock, then you get the result right there. So there's no need for me to click. And even without clicking, I'm happy. Also, in let's say you're looking at Wimbledon 2017 results, then Google just shows the results right there. So I get to know whatever my need was without even clicking. So this is where like just clicks and a lot of focus on clicks, which has been happening, is really bad because uh, clicks don't happen in these scenarios, and then we need to develop something else. So this is where like a lot of recent research has gone into saying that we are missing out on detailed user activity, like some sequences of interactions, which we should consider. So that's the goal of the next part of this phase, wherein we are saying that can we leverage and use user interaction sequences to predict user satisfaction? And essentially what we're going to say is that we're going to log the sequential interaction behavior of the user and then use that sequence to predict satisfaction. So far, we had just looked at the interaction and extracted features. The features were, has the user clicked or not? Or what's the dwell time? Has they scrolled or not? What's the average scroll speed? What's the maximum Y coordinate, minimum X coordinate, and so on. So far, we have looked at the interaction data, but we have only extracted specific features from it. Now we say that we can do a lot more. We can look at maybe sequences. We can look at motifs and like time series, and then maybe do a lot more predictions based on that data. So this is what the next part of this talk talks about, that how do we go from just extracting features to extracting sequences and motifs? So if you're looking at, there's this like preliminary work at Wisdom in 2014 saying that how do we discover motifs from cursor movements? So if you look at the image on the right, then the red design shows like how the user's cursor movement happened across the web page. So again, the goal is like, instead of engineering complex features like speed of scrolling, maximum width of scrolling, maximum depth, and all these things, then maybe we can discover common subsequences, which are called motif. And motif is essentially a frequently occurring sequence of cursor movements. So the problem here is that different users examine the web page with different speed. So some might move slow, some might move fast, and similar movements can appear in different parts of the web page, right? Like, I mean, you can do movements at the top, you can do similar movements at the bottom. So there are a lot of problems to solve when you're looking at motif data. And with these problems, like there are solutions as well, because motif is essentially a time series, right? So a motif would be what's your coordinate in the XY space of the screen with a time t. So once you are in the time series world, you can apply like flexible distance metrics, dynamic time dropping, and some of these like location invariance attributes to solve some of these problems. I'm not going to go into a lot more detail, but then like any and every work in the time series literature can be applied to motifs, and that can help us like better make sense of what is this like user interaction sequence about. Some examples of the motifs discovered on search result page and on the landing pages are here. So I mean, you can see that there are different patterns in which users interact with with their mouse cursors on the result pages. And I mean, some of the results showed that if you just look at post-click behavior, like those features which you were looking at, then you're going to do decent on your metrics. But then if you consider motifs together, then you're going to perform a lot more better. So the overall takeaway point here says that if you're considering these sequences and motifs from it, then this is kind of useful because you can better predict satisfaction, and correlation with your explicit labels is higher. So the takeaway being that, yeah, if you have access to motifs, then consider it. The problem with motifs is like, again, like it's a sequence of X, Y, T, and it's not really interpretable. We don't know what's going on. So if I have to develop a metric in the feature space, it was easy because I could say that a click followed by a long dwell time is a satisfaction signal. And a click followed by a quick back and a reading time of less than 5 seconds is a dissatisfaction signal. So with features, it's not easy for us to create some of these metrics, which is extendable to millions of users. But with motifs, we don't have any interpretation. We don't know what's going on. I mean, we can visually view some of these, but then that doesn't really tell us like, okay, can we create a metric out of it? It's really hard. So this is where like we did some work on how do we extend and go beyond these features, not by looking at motifs, but maybe by looking at interactive sequences. So we did some work at SIGIR. This is some of my work which I did while I was at Microsoft Research. And here we are looking at user interaction sequences. So each of these is like a search result page. So you can see that over here, this is a search result bar, search bar. You can type in the query, you'll get some results here. This is maybe the Wikipedia panel, some related images on the right, and then some results here. So the yellow dots over here is a sequence of the cursor movement. So if we have the entire sequence, then the problem becomes, how do we consider these interaction sequences and then extract some of these interpretable metrics from this? And a very important thing to realize over here is that there's a strong need for instrumentation. That we cannot do all this if we don't have like logging in place. So if you're working with like if in 2 months or 3 months time, if you're working with some of these product companies, startups, then it would be very important for you to drive home the fact that a lot of like logging is needed for us to do sophisticated machine learning modeling and interpretation and evaluation. So again, like instrumentation helps us to capture some of these signals. And once we have these logging, then we can create metrics, which are a lot more better than the metrics you will create when you don't have a lot of logging. So this really is something which, like, if you're interning and if you're working with product teams and companies, this is something you learn there, and this is something which is not really obvious when you're doing like an academic course, because these are the problems which we don't obviously face on a day-to-day basis when we're doing our academic projects. So again, like, so here, like, if you can look at some of these sequences, then the problem becomes like, how do we create subsequences and actions from it? So this is where we can define the action space. So instead of a motif was the cursor movement over a period of time. So this is x, comma y, comma t. And instead of looking at a sequence of XY positions, our approach was that maybe we should look at a sequence of actions. Now, the actions could be a click on an algorithm, a click on an image, a click on an answer, a mouse read, a scroll, move, you're pausing, you're issuing query, dwell time, quick back. So we can define the actions. And once you have defined these actions, then I can look at each of these sequences. I can look at these sequence and then create a sequence of action. So instead of creating a sequence of motifs, which is instead of creating a sequence of x, comma y over time, I can create a sequence of actions over time and then try to apply some of the same logic. So this is essentially what we end up doing. So we can look at a sequence like small pause, like the user comes to your platform, comes to your search engine, the user issues a query, and then there's a small pause. They understand what the result is. They move their mouse, they click on an image. There's a quick back. They move their mouse again. There's a pause, and they do a mouse read. So mouse read is something which we define as a horizontal line across a result snippet of length greater than 50 pixels and duration greater than 100 milliseconds. That goes from left to right, and it starts and ends inside an algorithmic result. So if you look at how users interact with search engine results, oftentimes these results give you a URL and followed by some snippet text. So often what people do is like they move their mouse cursor while they're reading the text. So this is something which we can capture. So we know the x, comma y, comma t of the cursor movement. And if I'm able to look at these over a period of time and then say that a mouse read happened, then I can understand that the user actually read the snippet. And maybe this is where the user got the answer. So again, like, it's up to us. We can define these actions at whatever granularity and sophistication we want. once we have the logging, then like we can just kind of go ballistic on this and like define even more sophisticated. But then like we saw that mouse reads are fairly common in desktop search scenarios. So then like, yeah, I mean, some of these examples, the other examples could be like there's a very long pause, you click on a result, and then you spend a lot of time. So this long dwell time. So again, like if you have 100 million users making 100 million search queries, for each of these search query interaction, you can create some of these sequences. Now, the problem is, how do we find the most informative subsequence from the sequence? So if you look at a sequence over here, it could be like you scroll, you pause, do a mouse read, you click, you come back, you move again, you do a small pause, you click, and then there's a long dwell time. So maybe this is an interaction which a user had with the result page. Now, how do we know that what is the like is it good? Is it bad? Like we have 100 millions of these. How do we find out which of these makes sense? So this is where we say that if you're looking at these sequences, then maybe there are like some subsequences, like the red ones. The red ones are informative, and the pauses and some of these movements in between are not really informative. So these can be skipped. These can be treated as noise. And then if we can remove it, then I'll get the most useful subsequence, uh, which I can then cluster across 100 million users and 100 million sequences and get some sensible results out. Now, so in this paper, we exactly solved this problem. So we presented a subsequence extraction algorithm, which I'm not going to talk about right now. But then like if you do that, then you're going to get some most informative subsequences which you can use. So essentially, what we can do now is we can look at the sequences. We can look at we apply the algorithm to extract these subsequences. That will give us the subsequences which correspond to this particular sequence. And using this, we can predict whether the user is happy or not. So when we try to do some of these experiments, this is on Bing and Cortana data from Microsoft. Uh, this is when I was working as an intern, as a research visitor with them a couple of years ago. So here we show that if you're just using some of your click and interaction features, then you're going to do like really bad. Versus if you're looking at some of these like interleaved sequences, then your prediction accuracy becomes a lot more better. And this also gives you a lot of like leeway into creating some of your metrics. So if you look at some correlations, then long dwell time is positively correlated. An interesting part is that some of these negative correlations are coming in from random mouse movement. So if you're moving, pausing, moving, pausing, moving, then that means like you're not really finding what you're looking for. So that means like that is a potential dissatisfaction signal. And we found a potential new satisfaction signal that if you move your mouse and then you do a mouse read, then that is a bit positively correlated with user satisfaction. So I can pick this up and then try to find this subsequence in all the interaction sequences across 100 million users. And that could be a new metric which we can use to evaluate. So again, a lot of this work is very useful for developing your metrics. So yeah, so again, a brief summary of where we are is that you've looked at explicit feedback, you've looked at implicit feedback, you've looked at sequences, and we've said that instead of just extracting these clicks and scroll features, maybe we can look at sequences. In sequences, we can look at motifs, which are a sequence of X, Y of your cursor movement over a period of time. And then maybe we can look at a sequence of actions over a period of time. And the goal of this all is to develop metrics, is to understand how good our models are. And this is what will guide like future model development, future machine learning effort, and kind of help like large scale internet companies evaluate how good or bad they're performing. So in the last 10 minutes, I'm going to focus a bit more on thinking about satisfaction models. Why do we need them? And how do we think about metrics? So an overview of what's happening is that let's just pick up a search system. So the step one is user issues queries, right? So these blue dots are the different queries the users issue. And Then maybe we can divide it into sessions, we can divide it into tasks, whatever we do, but we can enrich this information with the user interaction sequences. So we have logging in place, and we can log and attach with each query what was the corresponding sequence of interactions the user did. So now I have the query, I have what the user did, and then I could do a sequential model for predicting satisfaction. So we have looked at a few models, right? We looked at simple classification models or like a sequence aware model for predicting satisfaction. So we can predict satisfaction for each query, or we can predict satisfaction for a group of queries in a session or in a task. Whatever we do, we can look at maybe a classification model or a sequential model. But then we can predict whether or not the user was happy with all these like rec queries or not. Once we do that, then we can make broader claims about sessions and tasks. So in the previous step, we can do predictions for each query. We can combine them to make predictions about a session or task. And then we can combine even further to say that the user tried to do this task across like using 4 types of queries. And we think that the user was happy or not happy, like whatever the output comes out to be. So this is what gives us one label for this task. It could be a task, it could be a session, and we can apply these models at scale on all the historic data in the last X days. So let's say I look at last 1 week of data, and then I have a prediction model, and I apply it to predict satisfaction on each of these interactions across all users and all queries in the last 1 week. And that will give me, for each user session, it will give me a value that this is the probability of this is the value of user satisfaction for that session. So now we can average it together and compute this final metric that in the last week, this model performed this much. So what this means is that evaluating ML systems at scale means that the first step is user interacts. So you try to find out what their information need. Task is they kind of interact, you log these interactions, and then you use your interactions to predict satisfaction for each query. And once you do that, then you can aggregate these across different models. So let's say we have 2 variants. Let's say we have tried out a collaborative filtering approach, and let's say we have tried out a multitask learning approach. So for 50% of the users, we try a collaborative filtering approach. For the rest 50% of the users, we try a neural multitask approach. And then we let it run for like a week. So now the model runs for a week. We have these metrics which predict whether the user was satisfied or not. And then we do the average for both these A and B groups in the last 1 week. And then we compare which model performs better or not. So again, we can do this metric computation for some simple metrics like click, that which group of users are clicking more, which groups of users are streaming more, or which group has a higher dwell time. These could be metrics, or we could predict which group had more satisfaction. So a combination of all these will tell us like, yeah, the model B is performing better than model A or vice versa. So this is essentially what goes on behind the scenes across a lot of these like companies. What differs is what type of interactions and what type of signals, and what do you mean by satisfaction? What kind of labels do we assign? So across Google search, Amazon products, Spotify music, delivery food, some of these behaviors are going to change, but the entire philosophy and thinking around how do we learn and evaluate these models at scale is kind of similar. So I'm just going to, in the last 5 minutes, briefly touch upon some recent papers to give you a flavor of, again, I'm not going to go into detail in each of these or any of these. I'm just going to briefly mention it so that you can, if you're interested in any specific domain, you can pick this paper up, read it, and kind of follow the trail there. So in e-commerce search, there's a nice paper from Flipkart. So Flipkart is an e-commerce portal, very famous in India. And essentially, it says that how do we predict query performance in e-commerce search? So this is a SIGIR paper talking about product and like search and e-commerce platforms. We can specifically focus on product search and try to understand user intent and behavior and perceived satisfaction. So the satisfaction users have with general informational queries is very different than product search. So if you're on Amazon, then the kind of product search you do on Amazon will have different expectations, different interaction behavior. So this paper kind of focuses more on like product search and what kind of interactions and what kind of intents and behaviors and satisfaction metrics we could develop there. There is a Wisdom 2018 paper on image search, that how do people interact? Why do people search for images, and what does it mean? How do we know that the users are happy and not? So again, very similar to, philosophically similar to the kind of approaches we have looked at recently. But again, like in image search, there are like some domain specific nuances to consider. So this paper briefly talks about some of those. We can also talk about music discovery. So there's like some very good work coming out of Spotify, my colleagues, and this is looking at user satisfaction with music discovery. So if you use like a playlist like Discover Weekly, then how do we think about understanding user satisfaction for a discovery style music platform? So again, like this paper talks about like how do we think about Discover Weekly as a problem, and how do we evaluate that the user is getting new music to discover. So satisfaction around those is something which we have kind of looked at in this SIG-IR paper. So yeah, so that's kind of about it from this part. And again, the goal of this part was to leverage user interactions and say that how do we use these interactions to consider and build metrics and experimentation in like a number of these like large scale internet companies, which rely on implicit feedback to evaluate how they're performing. So the take home messages here being that we need to measure user satisfaction, and we could do that via explicit feedback or via implicit feedback. And we know like explicit feedback is rare, it's costly to obtain, it's small scale, whereas implicit feedback is obtained at large scale. So if you're doing your logging right, you have a lot of data to work with and a lot of data to train your ML models on, to evaluate your ML models across. Then another message is that if you look at interaction sequences, then they help in better predicting user satisfaction. And the reason why we want to predict satisfaction is because we want to develop metrics. And once we have metrics, then we can evaluate some of these systems at scale. And then if you have different models, different variants of different parameters of your models, different approaches to try out, then you can try to evaluate how these models compare. So essentially, like one interesting takeaway message could also be that when I was at Bing, I saw like their A/B testing metrics dashboard had like hundreds of metrics. So in at any given point of time, any of these machine learning engineers or data engineers in any company are running experiments, and they're looking at like hundreds of different metrics and how the performance goes up and down and how the different user behavior is impacted. And then eventually there are some key metrics which decide whether or not we're going ahead with this production change or not. So maybe some of your important metrics moved positively, and then you decide, yes, I'm going to push forward and deploy this model in production. Whereas if some of these other metrics are not moving that much, then it's not worth it to deploy this model. So let's just keep the current model. So these are kind of decisions which people in some of these like companies make. So the moment you kind of graduate and go and work with the industry in any of these like machine learning systems, then you're going to get exposed to a lot of this like experimentation metrics and evaluation style problems. So that is the goal of talking about this phase 3 in this lecture. Cool. So briefly summarizing what we have discussed today, we started by looking at understanding user task and need. And we focused first on web search, presented some ideas around understanding queries, understanding query intent. We then said that maybe query is not the right approach. Maybe we should look at sessions. So then we started looking at query sequences and like sessions, and then said that maybe session is not the best approach. Maybe a session can have multiple tasks. So maybe task is the right abstraction to think about some of these search problems. So then we presented like a few approaches to extract these tasks. We presented hierarchical approaches of extracting these hierarchies of tasks and subtasks, because some of these complex tasks decompose into more granular subtask. And we also said that like while in search domain, people do explicitly provide the search query. In recommendations, it's not that easy. So maybe the user never tells us what they want. So we'll have to infer it based on their interactions. So this is where like understanding user intent and goal is important. And if we can define user intents and predict it, then we see some better performance. So we considered a couple of case studies from Pinterest and Spotify and discussed how can we think about user need prediction, user intent prediction in some of these recommendation systems. In the second part of the talk, we talked about how do we learn user representations. So there are many different ways for learning representations we considered in this video. And some of these give you better results in some contexts, some of these give you better results in the other context. But the summary point here is that we can leverage the data we've collected about the user to learn a better model about the user. And this is going to help us do much better ranking and much better recommendation systems. And then eventually we talked about like, okay, how do we combine all these things together and then look at like, how do we like judge whether the user is happy with what we are surfacing or not. So the last part, which we just finished, was really talking about like doing metrics and experimentation at scale. So I mentioned this a few times. If you have questions, post it on Slido. Feel free to email me as well. And so my contact details are here. I'm readily available on Twitter at Irishab, and my Spotify email ID is also mentioned. If you're interested in some of these openings at Spotify in London or across the globe, feel free to get in touch with me on that as well. So yeah, thank you. Bye-bye.